So, hello everyone, this is Akshay here, and welcome to our GFG POTD streak of day 108. So, before starting the question, if you are new to this channel, please like, share, and subscribe so that we can learn, grow, and maintain our streak together. So, let's get started with today's question. Today's question name is BST Downward Traversal. It's an easy category question with points too. So, let's read the question and let's solve it with the different approaches if there are so available. So, given a binary search tree and a target value, you have to find the node whose data you have to find the node whose data is equal to the target, okay, and return the sum of its descendant nodes which are just vertically below the target node. Initially you are at the root node. If the target node is not present, BST then return -1. So let us dry run this first and second test case, what it is exactly saying. So if I restructure this tree, then what it will look like that the first node is 25, the second node is 20, and the this one is 15, right? The 20 left children is 22, so it just lies below 25, right? Similarly, 25 has the right node as 35 and 35 has the 30, so it just lies in the vertical level of 25 and 22, right? So the right children will be 45 and then the 30th right children will be 30, so this lies in this vertical line of 35, just below 35, right? So what I'm seeing is that this is my first vertical level, this is my second vertical level, this is my third vertical level where three nodes are there, and this is my fourth vertical level, and this is my fifth vertical level, right? So it is saying ki search for a node target 35. So let us search. We know that how do we search in a binary search tree, right? What we do that we will iterate for, let's say, while root is not equals to null. It's just a very simple code. What the binary search tree says is that if you have the root node as 25, then the left node will be less than the root node and the right node would be greater than the root node. So the searching becomes very simple, right? So if our root node is, let's say, if root dot data is less than target, right? The target is greater, right? So we need to search for the node which is greater than our root node. So the node which is greater than the root node lies where? In the right. So I will write root dot right. I will move in root dot right direction. Else if I will write if this inequality is reversed, that is root dot data is greater than target, right? So we need to move to the node which is having the less value than our root node. So I will move in root dot left, right? And there will be an else case that if the equality sign it will handle that the root data is equals to the target. So in that case, we will just break it from there, saying that we got a node, right? So running this particular code, this particular pseudo code, right? We will be coming to this node here, 35, right? Right or not? Okay, so we will be able to reach here. Let's say how we are reaching here. That root dot data is 25, right? And what I'm seeing that it is less than less than 35. So where I should move root dot right. So I moved in root dot right in a possibility that I will get a much greater node than 25, which will get equals to our target node. So we moved and the right node itself was 35, right? So if the target node and root nodes are equal, we break it here, right? So let's say we store this thing at root variable. What I need to do is that the nodes which are following exactly at this level, exactly as this level, I need to return the sum of those nodes. So in this case, I can see there is only one node which is the descendant of this uh, the the target node, that is root, and it was actually the target node, right? So the target node, right? So I just need to return this value, that is 32. So let's see the second test case how it is working, and then we will try to think of that how we can manage those vertical levels to get a sum of the descendant nodes. So if I draw the screen again for you, then it is be 20, 25, and 15, and 20 will have the 22, the right children, just below the 25. The 25 will have 35 as the right children, and 30 just below, just in this vertical level of this 25, 22, and 30. So the next node is 45, and 30 has the right children as 32, right? So let me draw the vertical levels now, which will depict that how many nodes are there in one vertical level. So this third vertical layer, as you can see, has the three nodes, 25, 22, and 30. This fourth one has the 35 and 32, and this fifth one, the last level, has 45. What it is saying to search for the 25 node. So we searched it and we got that 25 itself. The root node itself is the target node, right? The root node itself is the target node. So how many nodes are present in this vertical level just below it? So that is 22 and 30. So I need to return 22 plus 30, that gives us 52. So I hope you are clear to these points, that how the input and output are coming and how are we able to do the searching in BST. These 2 points are clear. So we are able to identify where the target is present now. And in the question it's written that if the target is not present, then return -1, right? So I will say I was iterating the root only, it's into left and right. So after the iteration I will say that root, if the root is pointing to equals to null, that means it cannot was able to find the target, right? So I will say just return -1. After this I need to write one more function which will handle the cases, which will handle and return the exact descendant nodes present in that same level, right. So the second thing is to function, let's say we will pass the target node here, right? The target node we just found. And what I need to found, there is one more thing I will give as variable as direction. So if you have studied trees while studying your data structures, so you must have come across a question of a vertical traversal of a tree. Vertical traversal of tree. So vertical traversal of tree says that for each and every vertical level, how many nodes are there, right? So if I found the vertical traversal of this tree, it will be 15, then 20. Then the third level have the nodes as 25, 22, and 30. Then the fourth level has the node of 35 and 32, and the last level is as 45. So what it is happening is the vertical traversal of tree. The intuition is, he in trees there is only one thing you do, that you always traverse in the tree using recursion, right? Either left or right, using the three orders, that is in order, pre-order, and post order. While traversing it, you just need to identify that what are the sorts of things that you have to do in traversing the journey to find, to reach our goals, right? So this vertical or traversal, what is the intuition is, when I'm at this root node, because the root node would be given to you, right? So I will mark this direction as 0, right? And whenever I move left, I will mark this direction as 1. And if I move further left, I will mark the direction as -2, right. And if I move right from 0 to right, then I will say that the direction is +1, 0 +1. And if I move further right, I will do +2. So since I have marked all these levels as -1, -2, and +1 and +2 for each vertical level, what I need to do, I just need to print all the nodes in the each particular level, and that will give you the vertical traversal of the tree. But in our case, what we need to do is, we do not have to do such thing, starting the 0, -1, -2 from the root node. We do not have to do that. We have to do it from the target node, right? So if I just dry run it for you, right? So in this tree, what was our node? What was our target? It was 25, right? So what will I do is, I will traverse left and I will do -1. So let me write the pseudo code for it. So I will say that if this is target, but let me write this, rephrase this as node, right? So I will say that if node is not equals to null, then I need to keep on traversing in my tree. So I will say that the function of what, node dot left, right, comma, since I went left, so I will say that value -1, or the variable which I use, that is direction, right? So I will say that direction -1, right? Then I will move node dot right, and since I moved right, I will say the value will be direction +1, right? And when I'll be at my root, right, I need to verify that if the node which I am here is, if it is not equals to the starting point, or let's say the target node, right? The target node, if it's not equals to target node, and the direction should be equals to 0, then what we will do, we will make a global variable and we'll add the node dot data. How this is working is, let me give you a very quick dry run for this thing, right? Let me draw the tree once again. So it was 25, it was 20, it was 15. 20 has the right children as 22, 25 has the right as 35, and the left as 30, and the right as 45. So what is happening here is that how I'm doing the traversal is that this is my target node as of now, right? Target node, and I am what I'm doing, I'm saying this, that this is my node, right? So I need to start it from here. So this is my target node, and whenever I found the target node, I will place that direction as 0, right? And I will, so this, all these descendant nodes which are having in this target, just below the target, will be in our answer, right? So whenever I move to the left, I will say that it is a part of -1. Whenever I move more left, I will say that it is -2. So if I move more left, it will be null, right? So our code does not, it has the base cases of to move left until and unless the node is not null, right? So how the recursion flow is happening is, first I'm going here, then first I'm going here, then first I'm hitting the null condition, right? And I'm traversing back, right? So if I it backtracks, so it backtracks to there, and since the 20 has the left call over, so it will go to this right call, right? And since here the parent call was having the -1, so it will do -1 plus 1. That gives us this direction as 0, right? Right? So left and right is completed. Now it will go back to its parent call again, 25. And since the left call are computed now, so it will move to right, right? It will move to right, and since it moves to right, it has the direction +1. So the parent call 25 has the direction 0, so it will have the direction as +1. Now the left call will compute, and since it is moving left, so it will be, the parent call was having 1, and it will do -1, so 1 minus 1, it will give as 0, right? It will give as 0. Similarly, the left call is null, so it will again backtrack, and the right call is also null, so it will again backtrack, and it will go to the parent call of 35. And since the left are always computed, the right will be computed as the direction +1. So the direction was +1 for this root node 35, so it will be +2, right? So as you can see that whenever I'm starting from the target node, all the values just below this vertical lever are also having the same direction, that is 0, that is 0, right? So what I will do is that I will say the answer plus equals to node dot data only if direction equals to 0, right? So I hope that is clear. But why I have made this condition here, node not equals to target? What is happening here is that I moved left. First I moved left, right? As you can see, from 25 to 20, 20 to 15. And when I came back to my parent call, that is from 15 to 20 and then 20 to 25. So this is also having direction of 0. But in the answer, I do not want this node as my answer. I do not want the target node also to be in my answer. So that's why I'm making this condition here, that if node not equals to target and direction is equals to 0, then only include that node data into my answer, right? I hope this thing is very clear to you. I have made the all the possible dry runs which I could to make you understand in a very detailed manner. So again, if you are new to this channel and if you like my content, please subscribe it so that we can make the new video tomorrow with the full energy. So I hope this is very clear, and let's decide the global steps that that we need to run. So the first step will be to search the target node in our BST, right? So this will be a step 1. This is nothing but if the node is less than the target, then we'll move in the right in hope of searching the node which is greater than the target, and eventually it will come equal at some point. So I have explained this code, right? I will not explain it again. And this is the second step, that we'll made a function to call if the target node is found, then we'll do this thing. Else, if the target node is not found, then we'll return -1, right? Okay. So I hope we we should start coding this thing. And what will be the time complexity? For the BST, for the step 1, we are just traversing. The worst case will be traverse all nodes, right? And if we found the target, then we will again traverse all the nodes, right? And we will sum only the nodes which has the direction as 0 side. So it will be O of n plus O of n, right? It will be O of 2n. And the space complexity will be, since we are using recursion in the tree, so recursive stack will have the worst number of nodes present in the recursive stack as O of height of tree, right? How am I saying that? That when we traverse from 25 to 15 and then backtrack, right? 25 to 20, 20 to 15. So these all nodes were getting stored in a recursive stack. And as you can see that this is the leftmost structure is representing the height of the tree, right? This is representing the height of the tree. This is level 1, this is level 2, and this is level 3, right? So I hope this thing is very clear to you. And if you look back to the constraint part, The constraint is given as 10 power 6, right? So for 10 power 6, what is the maximum time complexity that we can use is, the maximum time complexity we can use for 10 power 6 is, if you refer my chart, it is n log n, right? It is n log n. This is the maximum you can use, and you can use anything below it, let's say n, right? So we are using n here. So, and which is obviously less than 10 power 8, so it should get submitted. So if you do not know this power of constraint, you must watch this video of time complexity. It must be flashing up here now. So let's start with the coding section now, right? So first step is to search the target node in our BST, right? So I will write step 1, search the target node in BST. So I will use the same root as my pointer to traverse in my tree. So I will say that while root is not equals to null, right? And I will say that if root dot data is less than target, then I need to move in the greater direction, right? So in the greater direction is nothing but root is equals to root dot right? There would be else case, that else if case, which will signify that if root dot data is greater than target, right? So I need to move in the lower direction of root node, so that will point towards root is equals to root dot left, because in BST the root dot left is always less than the root node, and root dot right is always greater than the root node. Okay, so that's the case, and there will be else case which will handles the equal part, that the root dot data is equals to target. So in that case we just have to stop our iteration, that we have found our target node, right? So let's make a global variable here, right? Because in the recursive call, we need to compare with it, right? In the last if that was written, that if the target node should not equals to node. So let's say that we have found the target, and let's name it at target, right? So if the target has been found, then I will say, I will just reinitialize the target here, that target is nothing but the root, right? And one more case that was given in the question, that if the target was not found, right? If the target is not found, so before initializing it, I will check that if root is not equals, if root is equals to null, right? Because this root is actually pointing to our target, right? So if root is equals to null, then I will say that return -1. Else I will initialize it with my global variable, because I have to use this global variable in my recursion, right? Okay, so we have this thing, and we will, let's say we'll call a function. We will call a function, or let's say let's move in an in order traversal, since we are following an in order convention. So I will, let's say that in order, uh, pass the node that is the target, and I'll pass the node as target, and then what we will do, that I will do, uh, it will start with the direction of 0, right? That is it, and I will say that return answer. And answer should also be, I'll be making that also thing as the global variable. Long answer is equals to 0, let's say, right? And let's make a function for this in order traversal, and we will do some things when the direction is equals to 0. So let's make it, so it should be a void function, because we will be storing an answer in the global variable, right? So I will say that node int direction, right? And the base case will be that if node is not equals to null, then only we are traversing, right? So I will write it as, if node is not equals to null, then only do the traversal. It is very obvious. So I will call it as, since I have named this function as in order, so because we are doing in order traversal, that's why we should name the functions in the convention that you are following, in the steps that you are actually doing. So in order of, I will do node dot left dot, since we are going left, so I will say direction -1, right? Because that's the main cache here, to find the node which is actually the all the nodes descendant of our target. I will say node root dot right, and I will say direction plus one, right? Now we are at the point where our target node is, that is at the direction of 0, because we are doing in order, right? I explained to you that 25, we were first at this 25 with the direction as 0. We then moved to 20 with direction as -1, and then moved to again left with the direction as -2. So there will be a point where we backtrack, and we will backtrack again to be at our root node. At root node, there will be a direction as 0, right? So this root node should not be the target node, else in rest of the cases, that is this 22 and 30, we will add it in our answer. So I will say that if this node should not be equals to my target node and direction should be equals to 0, and for that case I will just add the datas of the node of direction 0 in my answer, right? So I hope this is correct. And we made this long answer as a global variable, because when you made a global variable outside the function, that variable is getting accessed by each and every function you made. Similarly, for node target, I made it global because I want this to compare in my recursion function, right? That is the reason I made that as global variable, and then I pointed it to the actual target node. I found it via searching in my BST. So let's compile and run. Okay, so there are some compilation error. Let me look into that. Okay, I have used the same variable two times, so that is why I'm getting an error. Let me see. Yes, so the mistake I did was I used this variable as target here, right? And I cannot use that because we are using this target variable inside the functions also. So then, since this is a global variable, it does not change. Like this global variable can be accessed with any of the functions, and that is what it was creating the contradictions, that which variable to access, right? So I renamed it as node tar, and I have simultaneously correspondingly I have changed the things in my code. So it is star of root, and I have passed in order of tar dot comma 0, and similarly here in at line 151 I said that node should not be equals to my target node, which is named as tar. We did the pre-processing, right? So as you can see, compilation and run is giving the output correct. So let's hit the submit button, because the time complexity is O of n, which is bounded by 10 power 8, less than 10 power 8. It should get submitted. So okay, let's wait for the results. So great, the code is successfully run. And let me give you a code walkthrough. The step one was to just find where the target is, and since this is BST, uh, so it was very easy to find, to search in this thing. And the time complexity is actually to search in the BST is login, not OFN, because we are not visiting each and every node. We are deciding for each at every level. We are deciding either to move left or either to move right. So it will be log of n. To be precisely say, it would be a height of tree, right? This will be log n. And similarly, when we do the in and the step two was to maintain a direction whenever you move in right or left. So that was, so since we moved in order traversal, and we computed, like we processed each and every node, and just at the direction of 0 we had this thing as our answer, right? So since we have moved each and every node, so it will be O of n. That's it. So that is it. So the overall time complexity should be log n plus O of n, right? But that is the worst will be O of n again, and space complexity would be the recursive stack that is taking, right? For this in order thing, that would be O of n again, like O of height of the tree, right? As it is mentioned in this expected also. So that's it. Let's meet in the tomorrow's Purity Street. And few last thing, that's my DSL repository. You can start and fork to get help with the source code, as well as that's my Instagram channel. You can connect me here, as well as on LinkedIn for any doubts if you may have. And if you have any doubts regarding this question or so, you can ask me in the comment section. And let's meet tomorrow for the streak of D 107, 108, 109 actually. So till then, keep studying, keep growing, and take care, and bye bye.